Thank you very much, and thank you again for attending this conference and also attending this session. Hope you're having a wonderful time here. And this will be a rather longer talk, but try to introduce you to many of the activities that we're doing at the R-CCS as the flagship lab, center for high-performance computing, AI, and also for quantum HPC. So we know we have about 40 or 30 plus or so research and engineering groups, and of course each group does it has its own scientific mission. And by the way, we're hiring, so if anybody's interested, you can look at our solicitations. So if you're good, if you want to work in Japan, please let us know. But there are collective efforts as a center that we are tasked to do in terms of mission of advancing the science of, science by, and science for computing. And one is to advance, obviously, computing towards the future. Of course, we see some wonderful products that have come out or coming out. But of course, we are always looking to advance, move forward as a research institution, developing technologies for next generation computing, making significant leapfrogging advances, and of course, making that proliferate into the industry and of course, for global deployment. And that's Fugaku Next. And that's, but several talks have been given. Sano-san will give a more detailed talk later about Fugaku Next. There's science of and by, or AI for science. And we're engaged in multiple activities with respect to AI for science. The core AI for science project we're involved in is the TRIP AGIS project, which is a RIKEN-wide AI for science project. In fact, it's fair to say that although there are lots of excellent AI for science projects that are springing up in various places in Japan, I think it's fair to say that as an institution, we have a very organized activity and RIKEN-wide activity, basically institution-wide activity in AI for science, and that's RIKEN. And that's one of the reasons why, for example, the MOU between Oregon, NVIDIA, Fujitsu, and us have been signed. And very much trying to, we'll make some announcements forthcoming of our involvement in projects such as the Genesis project, but also other international collaborations. And then there's hybrid quantum HPC that we also are embarked on. Of course, RIKEN has R-CCS, whom we collaborate with, and but they're basically building a quantum computer like that. So they're mostly physicists building new quantum gates and so forth. What we're tasked at is to actually, once quantum computers are made, how do we deploy it? How do we manage it? What are the algorithms? What are the applications? Much what the supercomputing centers do. Now, for conventional computing, we do both, right? We design, we build, along with our vendors, we deploy. So we do this at one center. For AI for science, it's kind of mixed. We do a lot of those too, but also we work a lot within RIKEN, especially like the bio centers or the material centers that also the main sciences that we work with. And R-CCS, since R-CCS, their focus is to build quantum gates, whereas our focus is more on the deployment and the application side. We work together, but we split our missions. Okay, so that's the large overview. For the remainder of the time, I will focus on several topics, but I spent a lot of time this time on AI for science, because that's probably one of the most important subject matter that people are concerned with. And moreover, I can't really talk about that detail about Fugaku Next, which is a lot of things are still non-disclosure. And also, I'll leave it to Sano-san and also Dan, who will talk about some of it, and Fujitsu, who will talk about some of these things. So, okay, so when we're talking AI for science, so, we have made significant progress in terms of AI in general. But when you think about it, a lot of the AI that are commercial, like Gemini, ChatGPT, Claude, etc. These are they deal with daily live data, lives that come from data that comes from daily lives, like audio, video, internet video like YouTube, images. But these images are like low resolution, like let's say 2,000, 1,000, or even a little bit higher, maybe a few thousand pixels in resolution, or of course text. These are abundant, generic, and also can engineer data to work better with the machine ML model, because at the end of the day, these are to directly serve the humans. Right? So to get your email, suggest responses to email, automate the business process, etc., or draw pictures of animated characters, etc. But for science is much more complicated, because for one thing, the data are very specialized. Right? So in some data, we don't even know how to tokenize them if you're feeding it to a transform-based model, or even like convolutional model. Sometimes they're very hard to handle. Sometimes they're very big. Each data set is not a terabyte. In fact, as I will allude to later, for example, if you have high-resolution images, each image can be a terabyte, can be terabytes. Or it could be very complicated, have very complicated structure that cannot be described in a textual way. And of course, they're governed by laws of nature. So, data that's in AI for science is, for one thing, there's a big gap between what the commercial models are targeted to be optimized for versus the scientific requirements that are required for conducting science with AI. So that's one big gap. And also, sorry, just skip. Also, the data are typically, a lot of these data are non-lingual. So when people talk about AI, they automatically assume they're talking about LLMs, but actually there are lots, or maybe like diffusion models, image generation models. But in reality, there are so many other models. In fact, most scientific models are not subject to linguistic description. Well, maybe they are, but the semantic summarization of these data are very, very coarse-grained. You call it a CT scan image, a CT scan image, but that doesn't say anything. Right? Or there may be some, I don't know, some region that looks like a tumor, but again, that doesn't really say anything. Right? No quantitative descriptions of anything. Whereas AI for science, or sometimes maybe, again, like ultra-high resolution 2D, 3D vision images. They may be something like physics-inspired neural networks or surrogates that reflect physical properties. They may be physical world models for like laboratory automation. Again, they have to, but these experiments, since they're doing physical experiments, they have to obey the laws of physics. Control optimization, or like inputs, multi-channel inputs, time sequence inputs, but these are like thousands, millions of channels. You could potentially be hundreds of thousands of time series channels. Or it could be various structures, from atomic structures, or even more subatomic structures, all the way up to, big, ships and buildings. And those are scales that traditional HPC has dealt with, right? You deal with very fundamental particles all the way up to, buildings, and AI has to do the same. And you have to do the generation. You might be solving inverse problems. You predictive modeling, patterns. Oh, well, by the way, these slides are attributed to Mohammed Wahib, so I just credit him. These are not, I'm just describing these slides. I give credit to him. So, and these appear everywhere. Okay? Complex images are not just simple images. There are complex spatial temporal data. And they appear in many scientific disciplines. And even if you take an image, they go from CFD to climate, weather, satellite remote sensing, synchrotron beam light. That's many, many, many applications in science. So what we're tasked at AI for Science at R-CCS is we're looking at those models. We're not doing much LLM work, let's say, to compete with Google's or Microsoft's or slash OpenAI or Anthropic. Those are, we may be using LLMs, but we don't compete with them to create yet another language model, which is kind of a difficult task. But rather, our team being RIKEN being a scientific institute, we focus very much on non-lingual scientific models or scientific models with their association with language models. And domains such as materials or medical or various types of other types of imaging, or things like climate, weather, or things like manufacturing, automobile car design or parts design, things like that. And in fact, it's been very successful, and we've been collaborating with DOE on this, on some of those matters. And we have, it's happy to say that for the climate Orbit 2 model, where in geophysics, Oak Ridge was working on this, and our team collaborated. And on Frontier, which has like 40,000 GPUs, they trained the ECMWF's 50-year accumulation of weather models to create this Orbit 2 weather model, and won the Best Paper Award at SC25 in November. And we won the award for several reasons, because for one thing, these ultra-high resolution images are just intractable when you try to train it or just handle it by conventional means. Because when you think about it, these are potentially, let's say it's a terabyte image. Let's say you're trying to feed it to be, you want to be handled by some transformer-based model to make it easy to do multimodal association. In which case you need to tokenize it and linearize it. But when you have a terabyte data, if you tokenize, maybe it's like 4x4, 6, 8x8, whatever, you're still left with tens to hundreds of gigabyte length input sequence. Now, if you take any model, commercial models, what's the maximum context length? Typically less than 1 million, or megabyte, or megatoken. So there is 5 to 6, 7 orders of magnitude gap between what the commercial models can do versus what we want to do in science in that context. Or you can argue, maybe you should use other types of models. Then, of course, those commercial entities don't build those models either. Okay. But we came up with a scheme, various schemes, actually multiple schemes, to allow significant compression in terms of being able to fundamentally reduce the complexity using techniques such as particle decomposition and space filling curves, which are, if you've done any of those areas in HPC, then we're familiar with it, but applied to these areas. And there are many others that allow significant reduction in the cost of training, of course, cost of inference. And moreover, this is applicable to many areas. Right? It's applicable to medical imaging, it's applicable to weather, climate, it's applicable to what we're applying it to, as I will speak very briefly, what Wahib's team is working on is work with the Spring 8 people and also road infrastructure people to deal with infrastructure like roads and bridges deterioration. So it's applicable to many, many, many areas. It's applicable to many, many areas where it's societally important, but many, many areas where we need fundamental innovations aside from what's being done in LLM space. Yeah, so again, Orbit 2, they came up with this reduction scheme. They also came up to operating directly on compressed row inputs, and also came up with ways to do condition prediction for reduced uncertainty, but blah, blah. For detail, please read the paper. But what I should say is without these innovations, this model like this would not have been realistic, even on the biggest supercomputers we have, like with tens of thousands of GPU. So even if Elon Musk brought 160,000 GPUs, it's still an intractable problem, unless we apply these fundamental techniques. Same with medical imaging. This is a very interesting area. Like again, we try to predict the deterioration roads. And traditional methods have been looking at surfaces, but of course, if you just take a look at the surface, it really doesn't tell you much. You really want to take the core samples and be able to predict and then try to make a predictive analysis of what the condition is really like. But actually, this is really difficult because if you take a core sample, you really don't know what's inside. So what we're doing is we send it to our light source, Spring 8, which is a synchrotron with a kilometer ring. Synchrotron, by the way, with a mountain in the middle, a small mountain in the middle, and then they come up with images. But firstly, we have to create a model. But unfortunately, there is no label data. Right? So we have to do. So they have to figure out how to do training. But unfortunately, these are ultra like 16K by 16K images, and there are like tons of hundreds of thousands or millions of samples. So how do you? And these are all on labels. How do you deal with that? So they came up with various schemes like hardware, mask autoencoder. I won't go into details. And they came up with various other innovations like reconstruction segmentation schemes in a way such that now to process each core and to do 3D reconstruction, do segmentation, etc., the model has been built, essentially. And also now that model is built, they can do these types of downstream AI tasks using 8% of Fugaku nodes, by the way, which is about 10,000 nodes, about more than 10,000 nodes of Fugaku. For these kind of tasks, Fugaku is pretty fast for AI as well. So they can process one sample every 7 seconds. So this means that if you have like 10,000 samples, it's still within tractable range. Again, they've done many work with high quality segmentation without labels and okay. I won't go into details in the interest of time. So that was one exemplar model. Different groups that we have are building different types of AI for science models. And they are, of course, very high end. They require methods that are linked to the actual physics, and they cannot be handled by commercial models. Now, you also need the infrastructure. So you can't just say, we have a model that's fine. We need ways to acquire the data. But the data volume is getting so big, we just can't leave it to the instruments to spit out data, and you have a manual operator. And you send it uncompressed over a wire, expected to show up at a supercomputer to process that. The earlier example, the core sample, again, these are, each sample is multi-terabytes in size, so about 10,000 samples of petabytes. So what do you do? So we're working with Oregon National Labs. We're working on various infrastructures to try to come up with a data pipeline so that we can, these massive data coming from these input sources, scientific input sources, can be handled more or less automatically such that they can be fed into the data processing pipeline of these massive AI supercomputers. So these are, it's been a very fruitful work where we do various things like data compression. We also try to add some of the processing to do some of the early data processing like data deduplication, and also feeding it to some small models for quick processing of data to attach, for example, metadata. But all these, and also some of the, and all feed it to, branch it out to different types of downstream AI subtasks. And these, by and large, will be controlled by AI agents. So, but by and large, these are necessary part of the infrastructure. Unless you have these types of both input and output, aside from the compute, which is AI, the infrastructure will be, well, again, will not be feasible. But these are a set of tools and also sets of infrastructure like storage, network, and also machines that do run the AI or do run data processing, all will be controlled by AI. Then we have various tools too. The team Oregon and Zurich and R-CCS, we have come up with a tool which had won the best reproducibility advancement award, which is like a PES paper award but focused on reproducibility at SC. And so this is to exploit. This particular one is to really look at the tool to control the numerical precision. So applicable to HPC, but also applicable to AI workload or AI middleware. So these kinds of tools are quite necessary as we, as the AI hardware specializes to lower precision with different types of performance characteristics. So being able to apply the latest and greatest AI hardware, but still and enjoy the performance benefits. Various things are necessary, including, for example, we do a lot of work with NVIDIA on emulation and Osaka scheme to sustain high precision numerical accuracy and performance. So that's one work we do with NVIDIA. This is on the work we do to actually try to control detect and control the accuracy with this when these modern AI's hardware is involved. And we'll try to come up, so team led by Jan Donke, also Oregon NSU, we're trying to come up with enable AI in HPC workflows. Because again, HPC workflows involve massive data, very complicated. How do you create a unifying AI workflow within the HPC environment? So these are some of the work we're doing. So when you take all these AI for science artifacts, something like this really starts to be emerging. This is a slide that was written by, again, Wahib and also Rio, but also I had some discussions with it. So you have the instruments, you have the Matsuoka, so you have all these tools which may be AI-enabled they may be through MCP server or something. And of course, you have various data that are coming out of different modalities and so forth. Then you have various foundation models. These are particular to that type of modality. Could be could be a specialized model. Right? Then we have a retrieval agent. Again, these are like these are maybe like agent-driven that would be driving the acquisition of data. And then we have a frontier LLM, which is not so much LLM, it's the intelligence, it's the AI scientist that will be taking all these elements and then trying to formulate science along with the humans. Because just having the counterpoint to this is just having LLM alone doesn't drive science, right? Because if you reflect that to a human being, right? A human being without any of these instruments, right? You can't really do much science. If you're a philosopher, yes, you can do it. But modern science requires all these tools, artifacts, infrastructures to deal with the natural phenomena. So you have a whole bunch of LLM, a whole bunch of AI, and these will be tied together. But again, the challenge is a lot of these science modalities are semi-structured, sparse, high-dimensional. So how to deal with that? And they're multimodal. You can't just deal with one data alone with a single model. You really got to have multiple models to deal with them. And then, most importantly, as humans understand these scientific data, instruments, and so forth, how do you get the LLM or the AI scientists that reason about these, have knowledge and reason about these data? But how do you add additional knowledge, sufficient additional knowledge, as if you're training a scientist? And how do you get the agents to use them? So it's not just a matter of having MCP protocol. You need to have agents understand all the sciences that are available in the models that are embedded in these very non-lingual scientific models. So that's the big challenge we have. And of course, we need this because we really need to, as was alluded to by our keynote speaker today, Kitano-san, my good friend Kitano-san, that ultimately we want to automate much of the science as possible. So this is not to say that we run out of, we lose our jobs and we go out to the pasture or go to the beach and drink cocktail all day. But rather, of course, we want to automate science where it can be automated and have the human mind focus on something that's more like outlier, more of an outlier situation. So much of the hypotheses, tests, assessment, report, question, study, and archiving can be automated. And but you need all these tools. You need an arsenal of tools that would be federated by the reasoning. And we have some cases where some of our teams are starting to build those infrastructures. For example, Yasushi Okuno, he's a doctor and medical doctor and pharmaceutical research by training, but he has a division in our center, a fairly large one, like 20 to 30 people. And what he's doing is, for a long time, he's been constructing a pharmaceutical pipeline. So the idea was, from screening, like compounds, from some medical diagnosis to then you try to diagnose what are the metabolic pathways, and then you do the compound screening to see which was effective at target, and you do all the downstream thing eventually to come out with the drug. So so he's trying to create this entire, as much as possible to digitize such pharmaceutical pipeline. So over the years, he and his team have built many tools, like many tools, original tools, and also has accumulated an arsenal of tools built by other biologists and drug design people. So now he has over 1,000 databases and tools that can run on Fugaku, can run on cloud, and so forth. But now comes LLM, and now comes MCP, now comes agents. So he says, okay, well, maybe we can, instead of a conventional workflow engine we've been using, maybe we can automate the entire process using AI agents. And that's exactly what his team had been doing for the past year. So now he has a working prototype where he can ask questions like that, a query, a research query to see, what about this problem, basically. And then the agent goes out and calls various tools. Remember, there are more than 1,000 tools at its disposal. And then it would output the result, not just a standard small response, but basically an entire paper, research paper. So So I don't know the validity of this because I'm not an expert in this, but apparently it's a fairly sound piece of literature, according to them. Okay? And moreover, something like this is already applicable to many domains. So it can be used in biological domain. And it can be used in chemical and physical domains like compound discovery for certain things, like certain viruses like COVID, or it can be used in clinical domain, more like kidney. Well, what happens when you injure the kidney? Again, because there are so much data and tools, but also that it's under. So we have all these tools and also smart and domain-specific AIs, combinations thereof. And then you have the intelligent AI, which is acting as scientist, drive the AI scientific discovery loop to be able to generate these types of results. So that's already coming. Right? And this will get better as the time goes by. So it's no longer, so supercomputing is like no longer about you have a single application, you submit a job, batch queue job, you get the result, and you do post-processing. Those days are pretty much gone. It's about AI model. It's about these agents. It's about formulating this workflow, the AI formulating workflow. It's about driving an AI scientist, driving the scientific loop of innovation. It's about that. And that's how, when we design a machine, that's what we will design the machine for. Okay? Not to run this big impact job, but to enable science this way. So again, we need to have these, data pipeline. Kento Sato and his team was working on this. Also need security because acquiring data and processing by AI is, of course, obvious thing to do and what we need to do, but there are lots of security questions because AI models can be, in some cases, can be a security nightmare for various reasons. Like there may be inadvertent leak of information because AI just suddenly decided to do so, or there may be some embedded threats which we don't know of, or there may be some commercial interests peeking out your data, etc. So in Dawkins and soon to be commissioned, our operational AI team will be building secure AI environment for training and also data ingestion and other downstream AI tasks. So while being easily accessible, so give it like OpenAI like interfaces or API-based access, but make it much, much more secure, right? So that people can acquire data and have security in terms of being able to train their data in a secure environment, even if they bring some models that may be slightly, not malicious, but slightly aggressive to leak information, the information stays safe within the firewall. So building systems like that, and this will run on on our new AI cluster, but also hopefully will run on Fugaku, and we'll have versions that run on the cloud. So what we want to do is put all these things together, okay? And for every use case, scientific use case, we want all these arsenal tools running on supercomputers, resources, running on large-scale storage, connected by high-speed network, but all the software artifacts, be it AI, non-AI simulation, various tools, a variety of non-lingual and non-lingual foundation models, all to be integrated and working together. So that's the sort of environment, again, that we're aiming to build, or we are building right now. And so with that kind of arsenal, that's the real infrastructure that we're aiming for. Right? That's the sort of infrastructure we're aiming for. Not so much, again, building this one giant big machine and running big scientific job. Again, those days are gone. They don't produce as much science as we want to, right? And so there will be a call out by Ministry of Science and Education to do real AI for science, not sprinklings. And so, of course, a lot of our teams will respond. But these are not, some domain scientists getting together and sprinkling a little bit of AI. What I call, in Japanese, I call it the furikake AI. Okay? If you know what it means. Let's say you have some domain that does things, and they're doing, let's say, some linear regression analysis on the data sets. And then we'll bring AI, we'll do SVM. So that's not sort of a thing that this 300 oku, or about $200 million call is intending to serve, but rather real AI for science schemes, some of which I demonstrated, but there could be others. But we really want to, I'm helping them to establish this call, and really want to advance AI. We want to advance AI for science in a manner that will really accelerate the cycle of innovation. He works on quantum, switch gears. So we're trying to build this multi-quantum computer, multi-supercomputer environment. And in fact, almost production environment, rather than just a tiny toy. These are serious machines. So we have two commercial quantum computers on-prem, and one experimental one, which is RIKEN. One is IBM System 2, 156 qubit. And one is a Quantinuum H12. It's 20 qubits right now, but it'll be upgraded to 56. We will also have a quantum simulator, both running on Fugaku, but also we'll have a new GPU machine integrated by ScaleWorks and Gigabyte, running with 540 GPU, Grace Blackwell 200 MBL4. So we have both real quantum computers, multiple quantum computers, and also simulated quantum computers. And of course, what we're aiming for is hybrid, because we're finding that just quantum computers alone will not be very efficient. There are a lot of, if you take any algorithm, there are portions that can be accelerated by quantum computing, but there are portions that are quite wasteful or even almost impossible to run on a quantum computer. So most real applications are hybrid. So we need classical elements, and of course we have Fugaku. And we have this GPU cluster. So we'll be combining this, and of course we need to put layers and layers of, multi-layers of software support, because otherwise people can't use them, to really implement a production level quantum computing environment, quantum HPC environment. Again, these are not toy, these are almost real production. In fact, we're doing this under the funding of an industrial ministry, not MEXT. And thus we have an industrial program where we have 20 companies involved, and all of them are creating very interesting quantum use cases, quantum HPC use cases. One interesting one I saw is like, they're just trying to do, one travel company is trying to do like travel plans, including like golf courses. Seemed bizarre to me, but there are some interesting things that people are thinking about. And we want to extend this, and as I may have seen in the MOU signing this morning, that we will try to collaborate with other centers to essentially try to create a global network of high-performance computers and quantum computers. And there are, although I can't go into detail because I don't have time, but I have strong convictions to believe that this network of high-performance computers alone did not make sense. And in the good days we tried that, didn't work. But if you combine it with quantum computers, for various technical reasons, it will work. So the goal would be to create a global network of high-performance computers and quantum computers hooked together to formulate a computing infrastructure of the future. So we'll try to build middleware to implement that. Of course, we deploy the machine. And we have real applications too, by the way. So this is work we're doing with IBM, where we use 77 qubits on their IBM System 2 and use 150,000 nodes on Fugaku to solve, do the matrix diagonalization, to observe the characteristics of a material for sulfuric substance. And we're almost approaching the energy level that was produced by classical means, so the MRG, which is kind of limited, but still. Seemed to work on this application. But as you can see in the graph, we're almost getting to the point where we're matching the MRG. So we're not quite there yet in terms of quantum advantage, but we're getting there very quickly for real material science application. Finally, Fugaku next. Again, Kentaro will give more detailed talk. But it's been, what I would like to say, it's been years. So, and also Aoki-san gave some talks with regards to applications. It's a massive effort. It is a massive effort, and led by Kondo in this division. Of course, I work with them to lead the charge. And we've been doing this for the past almost 3.5 years now, almost 4 years, starting from our initial studies. With all, many companies involved, of course, we had to down select to Fujitsu NVIDIA. But all in all, this has been a very fruitful collaboration. And will even be more, and I think several people will talk about it. So it's been covered extensively, and the announcement itself was covered extensively by the Japanese press. Got lots of, tons of media attention. But the most important thing is, even from the initial onset, we planned the project to be made with Japan and not made in Japan. Because in this global, for two reasons. One is we can't really build a competitive machine with the resources of a single country alone anymore. Even Fugaku, right? The K computer is almost purely Japanese, but even Fugaku, if you think Fugaku is a pure Japanese machine, it's not. It's an ARM processor. The fabrication was done in Taiwan, TSMC. The detailed design was done by Broadcom. Fujitsu did the basic design, circuit design, but the implementation was done by Broadcom. It uses Samsung and SK Hynix HBM. It uses NVIDIA Mellanox fiber and AOC for interconnect. So even Fugaku, and it uses, by the way, use Linux as the operating system, and it's R. Right? So even Fugaku is already made with Japan. But we really want to emphasize that it's made with Japan, but this time much more excellent technology on the Japanese side, made it with excellent technology on the this time with the US side, principally NVIDIA, to build a machine that's commercial, that's not only fantastic, so it'll be like a groundbreaking, hopefully it'll be like a groundbreaking machine of the time. So that's one reason we want to do it. We want to build something groundbreaking, and convergence of Japanese technology with US technology and other global technologies is the only way to go. And secondly, we want market penetration. The project needs to be sustainable. If you look at NVIDIA, why is NVIDIA the highest value company in the world? Because it penetrates and conquers the market. Why isn't Fugaku conquering the world? Right? This time we want to conquer the world. So Fujitsu is building what will likely be the best CPU, ARM CPU of the generation. It will be based on the Monaco chip you see on the exhibit floor, but it will have additional properties. And Fujitsu will describe it in more detail, but three things. One is it will be fabbed in 1.4 nanometers, so have lots of cores, high performance cores. It'll likely have fairly high memory bandwidth. I can't go into it why, but it'll have very good memory bandwidth. Secondly, it will have pretty high AI performance. Probably it may have the best AI performance as a CPU. So a lot of agents will be offloading tasks, who itself may be agents, AI agents, or may have CPU tasks, combined CPU tasks, can run beautifully on this chip. Right? And by the way, the demand for CPU is increasing significantly. If you think that AI is driving the demand for GPUs, yes. But if you think that there's dwindling demand for CPUs, are totally mistaken. AI, especially agents, are pushing up the demand for CPUs. Because at the end of the day, all the services are mostly run by CPUs or in combination with GPUs. So it'll have very good AI performance. Well, not to the extent of things like the top-end GPUs, but it have these very good performance as a CPU, AI performance as a CPU. And finally, it will probably have direct connection to the state-of-the-art GPU made by NVIDIA to be totally integrated. Or there could be standalone version of the chip. Or there could be a version of the chip that we've made it to other types of accelerators. Well, that's up to Fujitsu. But again, Monaco X will likely be the top CPU in the world and may see penetrations into the global hyperscaler market and selling in the million. Okay? Not tens of thousands, not 100,000, in the millions. And of course, this will be made with the latest and greatest NVIDIA technology, but Dan will talk about that. And of course, we will have a test bed. This time, unlike Fugaku, where people are just suddenly thrown into the Fugaku environment, this time will be, since RIKEN will be, as Aoki-san noted, if you listen to his talk, since we'll be taking charge in many of the aspects of system software, tools, applications, unlike Fugaku, where Fujitsu did most of the work. But this time, RIKEN will do most of the work. So for that, we need also the application teams to convert their software into GPU environment, and that takes time. So this time, we'll have a gradual porting and gradual testing of the software. So we'll be building a series of early test beds. And these will now also have production roles as AI machines or quantum HPC machines, so that there will be a smooth transition from point we have right now to when we deploy Flat Connects. It will not be, and we'll also try to make a lot of the information open. Finally, something like this is not without collaboration, international collaboration. So again, we have very extensive collaboration with Erie Labs. We're considering considerable collaboration with Europeans now that Japan is part of is part of Horizon 2020 with entities like RIPC. We have extensive, we're trying to extend our collaboration to Asian nations. Just signed an agreement with Singapore institutions. But again, we really need to, the world really needs to get together because the next challenge in building an infrastructure, again, which is not about submitting huge HPC batch jobs, but about this whole integration of agents and scientific workflows and the cycle of innovation being automated. That's a whole daunting task that we're faced with. And of course, we can't do it alone. It has to be done in collaboration. Okay, with that, I'd like to end, and thanks very much.